So I'll just introduce Professor Nori in the following words from this legendary writing of one. So this is how he talked about it. Nori, I'm quoting, Nori was a wonderful teacher and a very inspiring person. He did more than teaching. He created a wonderful ecosystem and developed a personal connection with his students. Who better to address us? I have
I'm really honored to be at this today. Today's talk is very inspiring. So, this is more like an industry person's talk. Very few words, few pictures, but I want to share my experience. What do we teach? How do we learn? Why do we teach? And what is the quality of education or learning that we imparted? And what is its value? This is what I will try to talk about as a part of my experience in this. Yeah, I am associated with IIT Hyderabad now as an adjunct after having retired. And I've been very lucky, I must say. Through my career, I've been affiliated with academic institutions all through, even though I worked for 6 years in the university. Okay, this is very pedantic. Teaching is a process. Industry people like processes because that's the way you organize yourself, you do a lot of organizing. Teaching is a process. So, as teachers, we are all engaged in the teaching process, and it is through this process that we provide instruction to our charges to the students. The learning in the students is the outcome of this process. So, for every process, industrial process, there is an outcome, a product or a service. So, there is a correlation between what we teach and what is learned, hopefully. And the student is the recipient of this instruction and acquires knowledge. Okay. So, I started teaching long ago because I had great teachers. I really loved them. They made the subject come alive. They were able to help us reason within the subject and become independent of them. I think that's the best thing that teacher can do. At the end of the course, you are no longer needed for the student. The student is independent and can work by himself or herself. So, to be able to reason about the subject and the problems that you are faced with is an important concern that as teachers, as a teacher, I try to convey. And as the fundamental said, some of my students like me. And but I never questioned myself. Was I a good teacher? Why was I a good teacher? Was it good teaching? I never questioned myself. I just imitated my teachers as much as I could. And whatever I liked in them, I tried to reinforce while I was teaching. And whatever I didn't like, I actually tried to dominate. So, for instance, some of the teachers used to be very harsh. So, I just avoided things that I felt were not right and reinforced the things that I loved from my teachers. And I taught all through. But for the past 13 years or so, I've been involved in using computer technology increasingly in education. In particular, around 2000, my boss, industry man, he said, why don't we use computers for doing some social good? Why don't we teach literacy there are 287 million adults who are past the schooling age, and they're illiterate. They can speak their language, but they don't know how to read or write. So he said, can computers do something good besides earning money for the company? So how do we use computers? Can we speed up? Approximately we need 2 lakh teachers. 2 lakh teachers are hard to come by. So if you cannot get teachers, can we give multipliers to teachers? Can technology give multipliers? That was the program that I was involved in. And like beginners love it work, whatever we did seemed to be acceptable. So even then I didn't think, what does it mean to be a good teacher? It was suddenly the problem of improving this technology that forced me to say, what is teaching, how do we improve it, what are the issues that concern us in teaching, and so on. What makes a good teacher? All the things that Mr. Govindan talked about, I started appreciating so late. But better late than never, even though I'm retired, I still try to teach at times. Not very successfully, but I try. Okay, so unlike doing things by yourself and learning by yourself and so on, and we need also good things to start off with. And there are two things that I learned or I valued a lot. There's a paper written by Beryl, a chapter in a book on principles of instruction. I have given these write-ups to Professor Kesav, and he may be able to distribute soft copies. Beryl's principles of instruction are, this is about how a teacher learns to teach. And what are the activities in teaching? And I have to learn from these principles in order to apply to building software technology for teaching. And the second part of the reading list is Bloom's taxonomy and learning and education. So Bloom, it's long ago in the late 50s or so, 60s, mid-60s, he started this taxonomy about what does it mean to learn? How should we organize our course material so that the learning is effective? And so this Bloom's taxonomy has been revised and improved. And so whenever we are talking about teaching, there are two parts. One is preparing for the course, preparing the course material, and the second is delivery. The first part, preparing the course, is all about understanding the subject and organizing and it's like a good textbook. But a textbook is just corpus of information, and it's not a process of teaching. It's a matter outside the teaching process, and the teaching process guides the learner through the corpus and makes it come alive. So the Bloom's taxonomy is interesting from the point of view of preparing, doing the course design. And the second part, that is principles of instruction, tells you more about how or what is involved in teaching. So I'll just detail these briefly, and after all this I'll come to software, which is the subject that I work in mostly. Merrill's principles of instruction says that he has these 5 principles. First principle is activation principle. It says all learning happens because you start with something that the person already knows. So whatever you are going to teach or put across must touch earth inside the student. So the first part is called the activation principle. Whatever you are going to teach, you activate it in relation to the knowledge that the students may have. So that is why it is important for us to have a homogeneous class with a similar background for all. So having activated the interest in the student because of something that they already know, then you need to demonstrate. I can illustrate these issues in other literacy programs. Activation principle says that we talk about words that people know already. Like in Hindi, the first word that is taught is makan. So everybody knows makan. You don't have to introduce that word. So you already know how to reach the student because they understand this word. There is no need of teaching the meanings and so on. It's just the sound and how you see it in scripted form. So activation principle is to use a word that people know. Demonstration principle says makan is no, ka, no. 3 syllables. And no happens to be also a simple phonetic letter, alphabet. And ka is a syllable. And so demonstration says, how do you join these sounds to create a word? and how do you look at these sums to see their scripted form. Application principle says from makan you can make kan, you can make man, you can make num, and you can make a few other words by stringing up the syllables in different ways. So the application principle says you learn something, apply it continuously to see you become familiar with it and you can use it. The integration principle says I learned that makan and then I heard a word called namak, and to and ka are different, and these are the things I learned. To, ka, no, and no. Task orientation principle says that we learn best when we apply what we have learned to a task which is told to us or which is common for us. So most of the time, for instance, you may have a laboratory course attached to your normal technical theory course, and the laboratory exercises you to work with the field, and it is the task orientation in the laboratory that makes us learn. As I said, I was in computing and software, and it is one of the strange engineering disciplines which is not concerned with material goods. Almost all traditional engineering is to deal with material goods. But here in computing and in particular software, we deal with non-material things and we have to engineer them so that they are not desirable properties. So the task orientation principle can be used in courses. I used to teach compiler construction, and the laboratory exercise, we have how to construct a compiler. That's the last problem that we have to solve by looking at the many topics inside the subject and knowing how to glue them together to produce the last. So task orientation can be exercises, can be quizzes, can be examinations where you solve problems, but also large problems which integrate across the entire subject's breadth and produce one large artifact. So, Merrill's principles of instruction, he says, here are two cycles that we use continuously. Whenever you start off a topic, you activate, demonstrate, apply, and integrate. This cycle is something that you apply to every topic. And this is how you can make the topic come alive. And the instruction subcycle, when there isn't any, when you have to cope with facts, for instance. Why is the fact there? What is the structure? How do you guide people to understand this fact? Like, if you have makan, how do you guide people to make more words with more, no, and so on? Guidance. Coaching. You help people. What is your name? How do you spell your name? How can you write your name? How can you prep graphical symbols? And so on. Coaching and reflection on what you have learned. This is the elementary part of Merrill's principles of instruction, where you come down to brass tacks and you have to deal with a specific problem. You go through this repeated cycle. Repeated cycles are very important because part of learning is delegating to the schools. And this is an important structure that we have to remember. Bloom's taxonomy thereafter actually tells us something more. It says while you're learning, there are three different aspects. There is knowledge that you have acquired and reason inside this knowledge. There is an attitude that you have to develop. I read long ago Herbert Simon, Nobel laureate and also a Turing Award winner long ago. He said that one of the things that he said about engineering education in the US, he said it is languishing because there is too much focus on engineering science. Engineering science says mathematize the empirical, and once you mathematize it, then it's very cheap to play with the ideas and come up with better formulations and do performance and so on. So he says engineering science has led us to believe that analysis is even more important than design. But the chief reason for an engineer is to do design. Every engineer should be designing things that are useful for others. And design is therefore an attitude that an engineer must have. An engineer must be able to produce artifacts which are interesting for people around. So this design as an attitude is an issue, and this attitude is not knowledge, but it is the way you want to think about the value of this knowledge. That is what is important. So attitude is important because it is only through inculcating attitude that you can get people to act on what they know. For instance, every program that we write is a tool for somebody because it simplifies some task. So it's a tool. So in some sense, computer sciences, software engineering is a tool maker's trade. And why do we need tools? We need tools because we want to lessen our work. We want to get mechanical advantage. We want to do this primarily because we feel that work is usually hard and we would like to simplify for ourselves and for everybody else around us. So, tool building is a part of the attitude that all computer science students must have because they must know how to help themselves when the problems are large and long. And engineering requires us to do a lot of design, so do tool design. Maybe what is the equivalent of the mechanical engineering machine tool industry for software people? In the mechanical in manufacturing industries, there are only a few manufacturing steps. They are repeatedly used in a variety of areas to accomplish most complicated things. So do we have the equivalent of such tools for software? Which is a language, which is a compiler, which is an operating system? What are they? So can we come up? They don't have to, even in mechanical engineering, they didn't come across these things through theory. They have come through empirical experience. And so we could similarly ask the same questions. So knowledge is important, attitude is important because we have to become engineers, not just get a degree in engineering. And to become engineers, you must be doing design. To become engineers, you must be using tools to make your work easier. And finally, we need skills. So skills is something that you have acquired by practice. Skills is it's a very teaching is about education, is about knowledge, and training is about skills. Skills can be immediately used. So skills can be developed through laboratories, through experimental work, and so on. So these are three aspects of knowledge, and Bloom's taxonomy organized knowledge in so many areas. He says that there are in every subject there are certain things that are new, so you have to remember them. In every subject, having understood something basic that has to be remembered, there are other things that can be derived. For instance, car is derived from per and r. So there are initially things that you remember, and then later on you don't need to remember them anymore because you can derive them. Once you can derive and remember a few things, you need to continuously apply them in order to build up the value of your knowledge. Then you are given a situation, you can analyze it. You can say, I heard na na. What is na? So it is no and ah. So I can analyze and say, I applied that rule which I learned from per to ka in order to make na na. So analysis is another important aspect, level of understanding. Evaluate. We have all our Indian languages and sounds, and suddenly we come across some word called bang. A is not a sound in any Indian language. So somehow you have to make that sound. So in Hindi you will say chandama or something like that. It is a codification of that sound with respect to the alphabet that we have. So evaluate says that there are things that cannot be done with what we know. So we need to extend our knowledge in order to know it. It could be the beginnings of research. For me, it has always been a very important cornerstone for attempting to do research. Whenever I taught a course and I found some areas to be very difficult, that was the beginning for research for me, how to make it simple. Or what are the essential ideas that can make it simple. That's not the only way research is motivated, but for me that was an important starting point. After you evaluate, then you have to create. So after you have understood that A is not a sound in Indian languages, then you have to create something. and then go on from there. So these are the many levels of knowledge. So if I put an exam paper, can I remember questions, understand questions, and so on, finally create questions. So people who are able to create, the rest of the class who are able to create, are the ones who have already started going beyond you. So you pose a problem in the exam and they are able to create, then you know that they should be getting their A grades. So I have used this in teaching at IIT Hyderabad. Courses on software construction and courses on principles of programming languages, to understand what is important and how students can go beyond what they have learned through questions that will dig into. So learning is just simply a planned outcome of teaching, and basically we gain knowledge. I have already said this quality of learning is how well does one perform with respect to team scale. But we focus on quality. Japan has such tremendous focus on quality, because that's the first step in engineering. The first step is to improve the quality of whatever we are making, and their quality revolution is something that we have to learn from and continuously exhort ourselves to learn how to apply to quality. Their needs for quality can be different from ours. The Sumit grinder for making idlis and dosas is not something that they would need in Japan. So this localization has happened, and we have to understand what is important for us, what is the quality that is critical, and make. Or the auto rickshaw is not something that is found everywhere except in India, Thailand, and so on. So it's the local needs that shape technology, and the value of engineering is in the solutions that we build for everybody. So quality is very critical, but it leads to value. And what is the value of learning? Is it the job? Is it the lifetime of employment? Is it the solution that the person is capable of producing? So there is value for applied knowledge, and that is what we are continuously focused on. And this value is understood only through individuals. We cannot have very broad classification. Every customer is an individual. In that sense, every student is an individual. It is for that student to appreciate what is the value of the knowledge. Though we can in general say what is worthwhile for doing design. That's really all that I have to say. Thank you. I don't know whether I have done any justice to it.